When we talk about databases, we usually picture a massive server humming in a data center, waiting for requests to come in. That is the traditional model. You have a client, you send a query, the server processes it and sends back results. But there is a different approach gaining serious traction. It is called DuckDB. And unlike the heavyweights you might know, DuckDB is designed to run inside your own application process. This changes everything about how data is handled. Here is the thing that makes DuckDB interesting from an engineering perspective. Most traditional databases, like PostgreSQL, are row-oriented. When you ask for data, the database reads one record at a time. Imagine a factory worker picking up individual boxes off a conveyor belt, checking each one, and moving to the next. This works well for transactions where you update a single customer order. But for analytics, where you need to calculate the sum of a column across millions of rows, this becomes incredibly slow. Every time the CPU checks a new row, it has to load that data into memory again. DuckDB flips this on its head with a Columnar vectorized execution engine. Instead of processing one row at a time, it processes vectors of data. Think of it as a team of workers passing a single long rope through their hands rather than passing individual boxes. The data is stored in columns, so when you need to sum a specific value, the CPU can load an entire chunk of that column into its cache at once. This minimizes context switching and maximizes the speed at which calculations happen. It is a fundamental shift from row-based processing to batch processing at the instruction level. Now consider the storage layer. Traditional databases rely on the operating system file system to read data from the disk. This involves a lot of overhead, specifically the standard POSIX interfaces for file handling. The file system acts as a middleman, translating your database commands into low-level disk operations. DuckDB has been experimenting with bypassing this entirely. Through a library called xNVMe, they can access NVMe solid-state drives directly. This removes the file system overhead completely. Preliminary benchmarks suggest this yields significant speedups, especially at larger scale factors. It is like driving a car directly onto the runway instead of going through the terminal first. Security is another critical pillar. In the past, encrypting data at rest or in transit meant paying a heavy performance penalty. DuckDB has looked into Intel SGX, which stands for Software Guard Extensions. This technology creates a trusted execution environment where code runs in a secure enclave. Even if the operating system is compromised, the data inside the enclave remains protected. Research shows that while encryption introduces under 2 times overhead, combining it with columnar compression keeps the performance usable. It is a trade-off that makes sense for sensitive analytical workloads where privacy is paramount. But DuckDB is not just about speed or security, it is about extensibility. The architecture treats storage and security as pluggable extensions. This means new features can be added without rewriting the core. Recently, this has opened the door for artificial intelligence integration. DuckDB is now being used to integrate large language models and retrieval augmented generation pipelines directly into the structured query language query engine. This blurs the line between traditional analytics and AI inference. You can query your data and run AI models in the same transaction without moving data to a separate service. This brings us back to the comparison with Spark or PostgreSQL. Spark is distributed and powerful, but it carries the overhead of managing a cluster. PostgreSQL is robust but row-based. DuckDB sits in the middle. It is an embedded database optimized for analytical workloads. It prioritizes in-process execution. This means there is no network latency between the application and the database. The query planning, execution, and storage are tightly coupled in a unified codebase. This allows for rapid iteration. Complex operations like filtering and aggregation can be pushed down to the storage layer more effectively because the engine understands the data layout intimately. Looking forward, the implications are clear. We are moving towards serverless, embedded analytics. The database internals are being optimized for ephemeral, high-throughput workloads in cloud-native and edge environments. It is less about persistent server instances and more about the speed of the query itself. DuckDB demonstrates that you do not need a separate server to get high performance. You just need the right architecture. The focus on direct hardware access and security adaptations yields tangible benefits. However, the broader foundational details of the internal architecture remain a work in progress. The current literature prioritizes specific use case optimizations over comprehensive documentation. Yet, the shift towards vertical integration between database and storage hardware is undeniable. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.